Okay, we're continuing on here, chapter 4. So last time in chapter 4, which is really sort of a continuation of chapter 3, we did our Vesper geometry. Remember, we did talk about really two types of geometry. We talked about the electron pair geometry, which describes how the electrons are arranged around the central atom. Again, when you're doing geometry, it's always the central atom that's most important. And we also talked about the molecular geometry. And that is also sometimes referred to as the shape as well. As we saw in certain cases, both of these names will be the same. And that is typically speaking when you have no lone pairs on the central atom. Because you have no lone pairs on the central atom, what essentially happens is those bonding electrons move. And because they are bonding electrons, they have atoms attached to them. And basically, the atoms will move just like the bonding electrons will move. And you end up getting really the same sort of shape for both the electron pair geometry and the molecular geometry. It's only when we start introducing non-bonding electrons, or dots, if you will, that we start to get a different molecular geometry name. Remember that really the worst case scenario in terms of repulsion is non-bonding near non-bonding electrons. Kind of the next worst is non-bonding near bonding. And probably the best in terms of repulsion type forces is bonding near bonding sort of situation. So definitely when we start introducing these non-bonding electrons, what ends up happening is we obviously have one less bond, for example, since we have those non-bonding electrons. And because of that, that allows really the electrons to get further away from each other as possible. And also because there's not like an extra atom sitting there in certain cases, it allows really those atoms to also move a little bit more. And what ends up happening is because of that, we do end up with a different molecular geometry name. The electron pair geometry will still be the same regardless of um, sort of how many bonds, non-bonding electrons there are. They're just based on electron pair. Remember that as well. The important thing when you do geometry, we count pretty much everything as one. So we count single bonds, bonds. We count double bonds. We count triple bonds as both one electron pair, and it will count as one bond. And that's really what you want to focus in on when you're doing geometry, is to go to the central atom. Again, figure out how many electron pairs, how many bonds there are, and obviously it will have a corresponding, obviously, geometries for each of those things. Remember that if you do have kind of more than one central atom, you basically will do the geometry for each one sort of separately. So you'd kind of put your hand over, say, the right-hand side here. You would still count this guy as you're doing it for the left. You would do the geometry for this guy, and then you would switch. You would then kind of put your hand over that side of the molecule and do the geometry for the other central atom. So if you have multiple central atoms, you could do the geometry for each central atom, again, just basically by separating them and looking at them as sort of individually different central atoms. Any questions on any of that geometry stuff there? As we also saw, we have some new geometries for a lot of you, probably, again, with those expanded octets. So we get into our, triangular bipyramidal and our octahedral sort of geometries, which is our 5 electron pairs, 6 electron pairs around the central atom. Any questions on any of that stuff there? All right, then continuing on here with our journey through bonding is we're going to talk about another sort of bonding theory. And the idea behind hybridization is this, that sort of valence bond model describes really covalent bonding as this overlapping of orbitals. And when we look at sort of the bond angles that we see in some of these molecules, just Lewis theory and Lewis structures doesn't necessarily adequately sort of describe the bond angles, for example, that we see. So this idea of hybridization comes up as another bonding sort of theory, and it accounts for a lot of the bond angles that we actually see and sort of the geometries that we see in these molecules. And the idea of hybridization is pretty much what it sounds like. We actually will combine atomic orbitals. And atomic orbitals are our S's, our P's, our D's, etc., going through there. So we will combine these atomic orbitals, and the idea here is, for example, if you just take your atomic orbitals, in theory, these are sort of the shapes, theoretical shapes. And if you were just to sort of have bonding occurring, for example, between, say, a p orbital and an s orbital, and maybe they're even on sort of different energy levels, it may not account for sort of the bond angles that we actually do see. So the idea is in hybridization is maybe we take these guys and kind of throw them together, and we go through a hybridization process where we make these hybrid orbitals that are essentially the same energy level. They also will share the same sort of shape, very badly drawn shape there, but they'll share the same shape as each other. And what that's going to sort of allow is for better overlap of these orbitals, because frankly, we're mixing things that are now basically identical to each other. They're also on the same energy level. So it makes for a better overlap. By the way, as we'll talk about, for every atomic orbital that you put in there, that's how many hybrid orbitals you get. So we took 2 atomic orbitals, we get 2 hybrid orbitals. That essentially happens. So this hybridization process allows for, like I said, for much better sort of overlapping, also sort of accounts for some of those geometries that we see. And again, for as many sort of hybridized orbitals that you make will equal how many atomic orbitals you basically put together to do that. Again, they will end up at the same shape. They'll end up on the same energy level, just going to allow everybody to sort of interact a lot better with one another. So let's talk about really the simplest hybrid orbital that you could have, and it is what is known as an sp hybrid orbital. So the idea here is we have s orbitals, we have p orbitals, d orbitals. So in this case, we're going to hybridize an s orbital and a p orbital here together. And essentially, as you can see here, the s orbital is kind of the spherical shape. The p orbital, right, is this sort of figure 8 type of shape that's happening there. They're going to hybridize, and they're going to form 2 hybrid orbitals. So the idea here is we took an s, we took a p. Those are 2 atomic orbitals. They will produce 2 equivalent sp hybrid orbitals. And as you can kind of see here, the shape a little bit is kind of like a kidney bean sort of happening here. It's sort of the shape. There's a little like lobe happening there on here. So we get these 2 individual sp orbitals. Those are 2 individual ones there through the hybridization process. Now, if we think about it, when we go through this hybridization process with the S and the P, that also means that we will also have these 2 p orbitals that are unhybridized. So we'll have some unhybridized p orbitals. In this case, the py, the pz orbital are unhybridized. Now, they will actually end up being 180 degrees apart from each other. And when we talk about hybridization and hybrid orbitals, they are related to the electron pair geometry. So they are related to that electron pair geometry. So S and P, dare I say, are 2 letters, right? So 2 electron pairs, 2 letters. That is related to the linear electron pair geometry, basically. Two electron pairs gives you that linear geometry. S and P, 2 letters. That's a nice way to tie those two together. That's how you could remember it. So if we look at this, for example, BeF2, and here we're actually looking at beryllium's electron configuration. We're really looking at the valence electrons here, 1s2 and 2s2. We're looking at these two valence electrons in this case. And what happens through the hybridization process, as you can see, we have our two electrons here in beryllium. We will get a promotion of a lower energy electron. It will actually work its way up into the p subshell. The result of that is we will now get basically an unpaired electron in the s orbital and an unpaired electron in the p orbital. And it's going to be these two atomic orbitals here that will go through hybridization. And because, again, we're combining two atomic orbitals, we will end up with two hybrid orbitals that are made. And as you can see here, we will end up with our two hybrid sp orbitals. Again, they are both the same energy level. They're both basically the same shape. These guys are then free because they have an opening in each of these. They are free basically to make a bond with the fluorines, basically. Share an electron with the fluorines there and make the bond that they need to. Again, you can see we have nothing going on really in our unhybridized orbitals in this case. There's no electrons or anything up here. They're just kind of hanging out in this case. So we could explain sort of this geometry here, which if I would do better would have been more linear across there, but we will have our two electron pairs here, and that will give us our linear geometry here. So the bond between our beryllium and fluorine is an sp hybrid orbital bonding to the fluorine. The next sort of hybrid orbital that we have is an sp2 hybrid orbital. And much like the name implies, here we're going to actually be taking two of the p orbitals and going to combo them together to make our hybrid orbitals. Once again, if you look here, you can kind of see there is our s orbital. And once again, we have a p orbital coming through here. We also have the second p orbital coming through over here as well. And because we combined, in this case, one s and two p orbitals, we end up with three equivalent sp2 hybrid orbitals that are made. Again, as you can kind of see down here, they all have the same sort of shape. And they all will end up being at the same energy level. When we do hybridize this, in this case, we will be left with one unhybridized p orbital that's not going to go through any type of hybridization. Here it is. That is 3 letters. Yeah, so that's like 3 electron pairs. So our electron pair geometry, that involves basically 3 electron pairs, is our trigonal planar. And that is a bond angle, as you can see here, of 120 degrees. So it will make this trigonal planar arrangement, as you can see there, triangle type of thing. So sp2 hybridization goes with the electron pair geometry of trigonal planar. And again, this is the easiest way to remember it. 3 electron pairs, 3 letters, sp2, right? So 3 and 3, yeah. Last one was 2 electron pairs, 2 letters, S and P. So quite easy to remember that way. Don't overcomplicate it. Again, here we're going to make basically 3 hybrid orbitals that will be equal in energy and provide for better bonding. So that is what we see here when we look at BF3, which is, again, an exception. And if we draw BF3, it looks something like this. And if we look at the electron configuration for boron, it's going to be 1s2, 2s2, and 3p1. And I feel like I missed it there, right? Yeah, there it is. And this is our 3 valence electrons that are present here. So we have 3 valence electrons. And same thing's going to happen here through the hybridization process. One of these lower electrons will get promoted upwards. And just like what we did with electron configuration, they fill these orbitals one at a time. So it will go to the orbital there in the middle, right? They all go in upwards, right? And then come back and pair up. So we go that way. That's going to allow now an electron in each of those orbitals, which are all 3 of them going to go through hybridization. And once again, since we hybridize 3 atomic orbitals here in boron, we will get 3 equivalent sp2 hybrid orbitals. We also have our pz orbital, which is that one there that's unhybridized. And in this case, the same idea. Each of these hybrid orbitals now have a spot to make a bond, and each of them will bond out with a fluorine, basically, and share an electron in that particular case. So sp2 hybridization goes with our 3 electron pairs. Questions on that there? Now, if we look at the next one, which is sp3 hybridization, much like the name implies, we're going to take our S and we're going to put together our p orbitals. We're going to combine all these guys together to make some hybrid orbitals. Again, there's the S and our 3p orbitals basically on there. And that will give us now 4, because we combined 4 atomic orbitals, will give us 4 equivalent sp3 hybrid orbitals that will be made. Again, they have the same shape, if you will. They will actually make this bond angle of 109.5 degrees. And again, we should be familiar with that. That is 4 letters. That's basically equivalent to 4 electron pairs. And 4 electron pairs is our tetrahedral geometry there. And that, again, is why we see 109.5 in terms of its bond angle. So things that have an electron pair geometry of tetrahedral will hybridize in sp3 orientation. In this case, we actually have no p orbitals left. They all get used up to sort of go through this hybridization process. And an example of that would be something like methane. And if we look at methane, once again, here we are making these bonds here. And if we look at carbon, which is 1s2, 2s2, 2p2, this is the 4 valence electrons that we see in carbon, which is this guy. And again, we're going to get that promotion of that electron, which will basically come upwards. And the result of that, again, is everybody here is going to have an electron in it. They will all 4 go through hybridization, and that's going to give us 4 equivalent sp3 hybrid orbitals, each of them with the ability to bind to a hydrogen, basically, a 1s orbital, basically, of hydrogen in that case. So tetrahedral electron pair geometry correlates to sp3 hybridization. Any questions on that there? Now, when we talk about bonds that form, that is a sigma bond, for example. And a sigma bond is a bond where we get basically what is referred to as sort of head-to-head overlap. Basically, the orbitals head right at each other and they kind of overlap each other. And in that overlapping area is where obviously our sharing of electrons go. That is what is referred to basically as a sigma bond. For lack of a better definition, you could think of all single bonds that are made as sigma bonds. Yeah, so really the first bond that's made in any type of bonding that occurs is actually a sigma bond. And that's a result of the orbitals, again, just heading basically straight at each other and going to overlap sort of head on in that overlapping. So if we look at a couple of examples here, we do see that hybrid orbitals do result in these sort of stronger bonds than these unhybridized orbitals. We could also see, for example, here, if we look at NH3, and if we look at the nitrogen, or we draw NH3, for example, we draw a Lewis structure for NH3. And we had to apply, for example, the hybridization that's going to occur with NH3. Here is how you do it, super simple to basically apply hybridization. You do this, S's, there's 1, right? P subshell, there's 3. D subshell, there is 5. So here's what you do. You basically do the exact same thing as you do when you're doing geometry. And when we do geometry, we want to look at the central atom, right? That is the most important guy. And when we do geometry, when we're counting up total number of electron pairs, there's one really important rule, right? And that rule is we count double bonds and triple bonds as single bonds, right? And single electron pairs. And that is how you want to count the electron pairs around the central atom when you're doing hybridization. So you basically want to do it the exact same way as you do it for geometry. So in this particular case, the total number of electron pairs around the nitrogen here is 1, 2, 3, and 4. So if I want to apply the hybridization to nitrogen, I do it exactly like this. I start with S and I just make some X's. So 1, 2, 3, and 4. I use what orbitals there? An S and how many P's? 3. This hybridization is sp3 hybridized. That's how you can do hybridization and pick it out correctly. So the nitrogen in this case is going to hybridize as sp3. Knowing that, we could look at nitrogen, which has an electron configuration of 1s2, 2s2, 2p3. Nitrogen has 5 valence electrons, essentially. So what's going to happen in the case of NH3 is we know it's going to hybridize through sp3 hybridization. So if we look at just the nitrogens, valence electrons, we got a couple of electrons there. Up here in the 2p, we got 1, 2, and 3 electrons. So we know that this guy is going to hybridize as sp3, and it's going to promote one of these electrons up. At this point, just like an electron configuration, where should this electron end up if it goes up there? It needs to go over here, right? It's going to basically promote into this orbital here. And that's going to cause us to have now 2 electrons like that up there in our 2p. We will have our 2s that has now just 1 electron in this process. When this goes through hybridization, which is going to hybridize as sp3, that means I frankly need to take everybody here. I'm going to take all those orbitals, which are 4 atomic orbitals. That will now give me 4 sp3 hybrid orbitals that are all equal in terms of their energy. I guess I can put energy this way. And we will have this guy, we will have this, this, and this. And again, this is nitrogen all the way across what we're looking at here. Now, what's going to happen is if we look at the bonds here in NH3, and if I number these bonds, I'll call this bond 1, this bond number 2, and this bond number 3. What's going to happen is now nitrogen has the ability to make a bond, and I won't draw this energy correct, but we have a hydrogen that has a 1s orbital that has 1 electron in it. By the way, hydrogen will not go through hybridization because it has just 1 electron, so it can't really go through hybridization. And it's going to allow it to make a bond here, and we'll call that bond number 1 between our nitrogen and our hydrogen. We will have another hydrogen 1s orbital that will be allowed to make a bond here with that sp2 hybrid orbital. And lastly, to be different, I'll go down because I'm running out of room. So I'll put the last hydrogen down here. Obviously not drawn correctly in terms of energy. But this last hydrogen there will be able to make a bond. And that would be like our third bond. So we were able to use, basically in this case, 3 of the 4 hybrid orbitals to make sigma bonds. And each of these would be considered a sigma bond. Just that little symbol there, sigma bond. Now, what is left when we look at our hybrid orbitals? We have a hybrid orbital right here. Can that guy make a bond? This hybrid orbital. The answer is, how many electrons can you put in an orbital? 2. Still the same rule applies. So can this one that I just circled, can it make any bonds? It cannot. So those 2 electrons account for what's left on our Lewis structure, which is when I go to nitrogen, I have 2 electron lone pairs. So those 2 electrons count for the lone pairs that I see on my nitrogen. So here hybridization accounts for all the bonds that we see in this Lewis structure and also all the lone pairs that we actually see in this Lewis structure as well. Any questions on that there? So hybrid orbitals can be occupied by bonding electrons. They also can be occupied by non-bonding electron or lone pairs like we see here in our NH3. Now, NH3 is electron pair geometry tetrahedral, right? And that makes sense as 4 electron pairs means electron pair geometry is tetrahedral. Its molecular geometry is trigonal pyramid. So remember that hybridization goes with the electron pair geometry, not the molecular geometry. So it goes with the electron pair geometry name. Question on that one there. So let's take a look at water and sort of see what's going on here. So if I have water, we draw a nice Lewis structure of water. So you take a second and decide what is the hybridization of the oxygen. Okay, so let's take a look. Again, we want to focus in on the central atom, almost like how you do geometry, since it is related to the electron pair geometry. That would mean I got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So once again, if you're not sure, just start at the bottom here. 1, 2, 3, 4. So that is an S and 3 Ps. So the oxygen here will also hybridize as an sp3 hybrid orbital. Yeah. That is as simple as you could get it. Count electron pairs and mark them off the boxes, basically, yeah, in terms of hybridization. So what's happening here in the case of water is we got a lot of, we got some bonds happening. We have some lone pairs happening. So if we look at the oxygen's electron configuration, 1s2, 2s2, 2p4, oxygen has 6 valence electrons. And if we look at it here, we have our 2s and our p going on here. 1, 2, 3, and 4. So what's going to happen again as it goes through this hybridization process, we're going to promote this electron up. And just like an electron configuration, it's got to go into that orbital right there, right? So again, one at a time, coming back and pairing up, right? Everybody at that point. That will get us here. We will end up now with a couple of electrons in those, one of those, and a electron here. And again, this is our oxygen. Now, knowing that it's going to hybridize sp3, that's going to take all 4 of these atomic orbitals And again, since you hybridize 4 atomic orbitals, that's going to give you 4 equivalent sp3 orbitals at the same energy level. And in terms of our electron count here, this is what we got going on. So again, if we sort of number the bonds here in water, we'll call that bond number 1 and bond number 2 in this case. We could see that we actually only have 2 hybrid orbitals that's available to make bonds, right? Because these guys here on the right only have 1 electron, which means we can make a bond with hydrogen's 1s orbital that has 1 electron, going to make, say, that first bond that we see there in water. We could also make another bond between another hydrogen's 1s orbital, which would account for those second bond that we see in water. Now, again, we can see that we had some hybrid orbitals right off the bat here that were full. And both of these hybrid orbitals account for the non-bonding electron pairs that we see on the central atom. So these account for those guys. So once again here, you can see that hybridization accounts for all the electrons that are present on the central atom. Again, both bonding electrons and non-bonding electrons as well. Any questions on that there? Yeah. We actually can go further than 4. We'll talk about it in a second. But when we get to we can talk about it now. Actually, here it was. Yeah, do it here maybe. So basically, the idea here is the relationship between hybridization and our electron pair geometry is we can definitely go above that. So basically, what we saw first was the simplest hybrid orbital you could get is comboing 2 atomic orbitals together. So that is 1 and 2. So that's basically 2 electron pairs, which is our linear. And again, this is our electron pair geometry we're talking about here. And that will get you your sp. As we saw, if we add 1 more atomic orbital to it, we will get 3 sp2 atomic orbitals, which are trigonal planar, and we'll get our sp2. We add 1 more like we just kind of ended up on there. That is 4 electron pairs, which corresponds to our tetrahedral, which is sp3. Remember when we did geometry, after 4 comes 5, yeah? And that will now get us into the D, right? This is our expanded octet, right? And that is our triangular bipyramidal. And that is the same deal. I have an S, right? I have 3 P's, and now I added a D to it. So it will hybridize sp3D. I personally write it this way. Books and stuff sometimes will put the D in front, so you'll sometimes see this written with the D in front. I personally prefer this way, but you will see it the other way written as well. And the other sort of geometry that we had in terms of the expanded octet was 6, right? Which should take us up to here. And that would be 6 electron pairs, which is our octahedral electron pair geometry. And again, 1s, 3 P's, and 2 D's. And that will give us our sp3d2 hybridization. Or again, sometimes people will write it sort of like that as well. That for us is as far as we'll go. We'll get into the expanded octets. And again, it just continues on this way. But if you just need to identify the hybridization, this is probably really, again, just the simplest way to do it. You probably will never screw up. You just need to count electron pairs. Again, doesn't matter if they're dots or lines. Double bonds, triple bonds still count as 1. And really just mark out how many electron pairs you have, and then you'll have really your hybridization that you need. Question on that there. So let's talk a little bit about what happens when we do have perhaps some double bonds or maybe even some triple bonds that sort of get into the play. Does hybridization account for everything that's going on in those type of situations? So if we have something like C2H4, if you draw the Lewis structure here, you will end up with something that looks like this. And in this particular case, we actually have two central atoms, right? We have a carbon on the left and a carbon on the right. So we actually have two central atoms. And what I'm going to do is I'm just going to number these carbons. I'm going to call carbon on the left, carbon 1, and I'll call carbon on the right, carbon number 2 in this case. So what you want to do here is figure out the hybridization. So why don't you take a moment. So for carbon 1 and carbon 2, what is the hybridization? Again, you do it the same way as we do geometry for each central atom. So do one at a time and figure out what you think the hybridization is here for each of those carbons. Okay, so let's take a look. We'll start with the carbon 1 on the left there. So remember, we basically just want to, if we can, put our hand over the right-hand side carbon, basically. Remember that the bond coming into that carbon on the right still counts for the guy on the left. So we basically have one electron pair, right? Two electron pairs, and my double bond counts as how many? Just one, right? So just like what we do for geometry. So we essentially have three electron pairs there for our guy on the left, which means 1, 2, 3. That means the hybridization of carbon number 1 should be an S and two P's. So that's an sp2 hybrid orbital. First off, any question on that one there? Now we're going to do the same thing. We're going to put our hand over the left-hand side. And again, still counting the bond that's going to the guy to the left for the guy on the right. And what we will see is 1, 2, and once again, counting as just 1, it'll be 3 for that guy. That will give us the same 1, 2, 3. So the hybridization here of carbon number 2 is also going to be sp2. So both of these carbons will hybridize as sp2. That is 3 letters. That is 3 electron pairs. That is trigonal planar electron pair geometry. That's a 120-degree bond angle happening here in the triangle type of situation. So let's take a look at sort of all the bonds we got going on here. And yeah, maybe I'll redraw it here. Draw it. So I'm gonna number these bonds here. We got 1, we'll go 2, we'll go 3, we'll go 4. And obviously a double bond has 2 bonds, so 5 and 6. So we'll number all those bonds. And now we're going to use hybridization here to basically help us understand how all these bonds sort of come together. So if we take carbon, its electron configuration as we saw before, 1s2, 2s2, and 2p2. That again is the 4 basic valence electrons, and each of these carbons are the same, so they both basically have 4 valence electrons, carbon 1 and carbon 2. And that means that if we just look at what's going on as we saw previously, we will get our guide to come upwards and promote. And in this case, we will end up with an electron in each of these p orbitals and 1 electron here in the s orbital. Because these carbons are going to hybridize as sp2, how many of these orbitals should I take through my hybridization process? sp2 is how many letters? 3, right? So we're going to hybridize only 3 of these guys, not all 4 of them in this case. And what that's going to give us for carbon number 1, I'm going to write it towards the bottom here. Carbon number 1, we will now get 3 equivalent sp2 hybrid orbitals that each have one electron in them. And what did not get hybridized for this guy? We have one p orbital that is unhybridized, right? So in this case, we still have that 2p orbital that's unhybridized. And it still has an electron, which means it's probably important since it's got an electron hanging out in it, right? So that's what's going to happen with our carbon on the left. Any questions? Carbon on the right is identical to it. So it's going to end up in the same arrangement, right? They both are hybridizing sp2. They're identical. So our carbon on the right-hand side here will also end up with, just for the same reasons we just did, 3 sp2 hybrid orbitals that each have an electron in them, and one unhybridized 2p orbital that also has an electron. By the way, we actually know what p orbital that it's not hybridized, because this is really px, py, and the pz orbital is actually the one that is not going through hybridization. All right, so this is our arrangement of all the electrons in the carbons, the carbon on the left and the carbon on the right. In addition to those carbon electrons, right, we have basically 4 hydrogen atoms hanging out, right? So I'm just going to draw the hydrogen atoms to the right and left of these guys. So we have I'll do it here. We have a hydrogen atom that has a 1s orbital with 1 electron in it. We have another hydrogen atom that has a 1s orbital with an electron in it. On the left-hand side, I'll kind of draw it like the picture. We have a 1s orbital, and we have another hydrogen that has a 1s orbital. Again, hydrogen will not hybridize. That is each of the hydrogen's electrons, basically, in this picture. Any questions so far? We now are ready to essentially make our bonds. We can see that all of the carbon hybrid orbitals are available to make bonds, right? Because all the carbon hybrid orbitals only have 1 electron, which means they can take another electron to make a bond. So we'll start with bond number 1 right here. That is between the 1s orbital in hydrogen and the carbon number 1 sp2 hybrid orbital will make bond number 1. Bond number 2 is also between the 1s orbital and the sp2 hybrid orbital in carbon number 1. We have basically the identical bonds on the other carbon on the right-hand side. So bond number 3 would be from the 1s orbital in hydrogen and an sp2 orbital here in carbon number 2, as that's carbon 2 and that's carbon 1. And lastly here, bond number 4 would be a result of, again, a 1s orbital hydrogen and a sp2 hybrid orbital. That accounts for all of the bonds between carbon and hydrogen in this case. Each of these bonds, these are all sigma bonds. Yeah, they're all basically sigma bonds. All these orbitals are coming straight onto each other. They're all going to do head-to-head overlap, and that's going to make a sigma bond. What bonds are left in my picture? Basically, what is left is the double bond, right, in the middle. So we have the double bond that's in the middle. The good news is, if we look at our hybrid orbitals, in each carbon, there is a hybrid orbital available to make a bond between the carbons, which is good because bond number 5 is between the 2 carbons, right? Which means that is going to be these 2 hybrid orbitals bonding right here to make the first line of your double bond, basically, yeah? And that also would be a sigma bond at this point, right? I am down to 1 bond left, and I only have what orbitals available to me to do that? the unhybridized orbitals, right? They have an electron in each. And that is where the second bond, if you will, for the double bond will actually come from. It will come from the overlapping of these unhybridized p orbitals. And this bond is what is known as a pi bond. Yeah, this is actually what is referred to as a pi bond. Why is it referred to a pi bond? Guy was hungry that day. No, just kidding. Bad joke. Thanks for not laughing. So this is a pi bond, and it's a result of a different type of overlap that's happening. So remember that the sigma overlap is when the orbitals basically just come straight at each other, head to head, and they overlap. Because we're dealing with, in this particular case, unhybridized p orbitals, I'm gonna drop it in right here, I think. Maybe. There you go. We have basically our p orbitals that are unhybridized, which means we have a p orbital for carbon number 1 that looks like that. And we have another p orbital, say, for carbon number 2 that looks like that. And the way that these p orbitals overlap is they actually overlap what is referred to as sideways overlap. Above, you can think of this as being the plane. Probably shouldn't draw a line there, but you think of this big part here as the plane of the molecule, of the bond, and it's overlapping above and below sort of the plane of the bond, and that's what makes basically your pi bond occurring in that particular location. So I'll get rid of that. Look out there. And that is basically what a pi bond. So a double bond, as we see here, is made up of two bonds. It's made up of a sigma bond, and it's made up of a pi bond in this case. And those two types of bonds is what makes up a double bond. So again, you can think of a sigma bond as like the first bond, kind of like a single bond. It's the first line that you draw, and that's always going to be like a sigma bond. Now, if you need to make a double bond, you'll need that first line, which is a sigma bond, and then you'll have these overlapping unhybridized p orbitals that make the pi bond. Any questions on that there? So once again, here we have accounted for all of our electrons here through hybridization. Now with double bonds, we were able to account how that occurs. Questions on any of that there? So let's talk about what happens when we have triple bonds. So once again here, if you draw this up as a nice Lewis structure, you'll have something that looks like this. And we'll call this carbon 1 and carbon 2. So once again, in this case, figure out the hybridization of carbon 1 and carbon 2 in this case. All right, so let's take a look. Again, we're going to kind of block off carbon 2 to start with and just look at carbon 1. Triple bond going to count for carbon 1 as well. So it's got one electron pair, and our triple bond count is how many? Just one, right? So basically, one electron pair, two electron pairs. That means that the hybridization here of our carbon number 1 is going to be sp hybridized. Basically, 2 is 2 electron pairs, linear, right? So geometry. If we look at carbon number 2, it has one electron pair, and once again, this guy is going to count as only 1. So again, 1 and 2, that also is going to be sp hybridized. Any question on the hybridization there? So if we take a look at what's going to happen here, all right, so if we look at the hybridization here, which is going to be sp2, again, carbon still has its 4 valence electrons. So in this case, we still have the carbon 1, for example, and here and here. We're going to get our promotion that's going to come up here to our empty spot, and that will then give us an electron in each of those along with our 2s electron. And since it's only going to hybridize in this case as sp, that means I really should only grab these two orbitals, right, to go through hybridization. That's what S and P stands for. Two atomic orbitals are basically going to get hybridized. Because I took two atomic orbitals, that again, I'm going to draw towards the bottom so I have a little bit of room. We have two equivalent sp hybrid orbitals that were made. They each have an electron in them. In this case, though, how many unhybridized orbitals do we have? Yeah, we have these two here that are unhybridized, right? And they still have an electron in them, which makes them probably important as well. So we have our two p unhybridized orbitals here as well. And that's really like your py, pz type of orbital sort of happening in this particular case. Now, because carbon number 2 in this case is identical, we will get basically the exact same arrangement there for carbon number 2 in this particular case. So I'm not going to go through it again. I'm just going to redraw what we got going on. We will have our same sp hybrid orbitals. We will have our two unhybridized p orbitals, which each have an electron in them, basically. So again, that is all of our electrons for our carbons in this case. Now, when we look at our original Lewis structure, we'll just number some bonds here. We're going to call this bond number 1. We'll call this bond number 2. We'll call this bond number 3. The middle guy we'll call number 4. And the top of the triple bond we'll just call bond number 5 in this case. So we can again account for what's going on in terms of all the bonding. We have obviously as well our hydrogens, which are going to supply one electron, right? So over here we have a 1s orbital for our hydrogen. And over here, for example, we'll just put it over here. We have a 1s orbital. So we know that bond number 1 is between carbon number 1 and that hydrogen. They're going to make a bond right there. That is a sigma bond, yes? And that would account for bond number 1. We also see that bond number 2 will be a bond between carbon number 2 and that hydrogen, which will be right there. That also will be a sigma bond. At this point, right, the only thing left is my triple bond. And just like what we saw with our double bond, we should also have a bond between the two carbons, right? And that is going to be really our very first line in our triple bond will be a bond between the sp hybrid orbital and carbon number 1 and the sp carbon, our hybrid orbital and carbon number 2 will make our third bond also a sigma bond, yeah? So if we just sort of blow up our triple bond here, this is bond number 3, bond number 4, and bond number 5. We just took care of our third one. We already know that our double bond or second line is a result of the p orbitals overlapping. So that would be a result of these two doing this sideways overlap because these are unhybridized. And that will be our pi bond in this case, which is bond number 4. So what is left to make the triple bond at this point? Another set of unhybridized p orbitals, right? So that is where the triple bond comes from. This is also going to be a pi bond as it's going to sideways overlap and we'll make our triple bond. So in this case, you have two sets on each carbon of unhybridized p orbitals. And this is where I really wish I didn't fail art, but I'll try my best here. So we got one set of p orbitals in, say, the py direction in three-dimensional space. And we'll go with this one maybe. And you have another set of p orbitals on, say, the pz arrangement. And what's going to happen is those guys are going to overlap, making one of the, say, double bond. And then we have our other guy doing a little sideways overlapping to make our triple bond. So you have these two unhybridized p orbitals in each of the carbons, going to do again this sideways overlapping of those orbitals above and below sort of the plane of the bond, and that's going to create basically two pi bonds. So when you have a triple bond is essentially made up of one sigma bond and two pi bonds, basically. And again, the pi bonds are coming from those unhybridized p orbitals. Any questions on that there? No. So basically, a single bond is a sigma bond. A double bond is a sigma bond and a pi bond together. And a triple bond is a sigma bond and two pi bonds that are happening. Question on that there? Yes. All right. So as I mentioned before, that one we did there. We just did our hybridization with our multiple bonds, double bonds, and triple bonds. And again, our pi bonds as a result of those sideways overlap, and we get a different sort of overlapping than we do with a sigma, which comes basically straight at it. So as we can see, hybrid orbitals can basically account for bonding electrons, can account for non-bonding electrons. And again, our multiple bonds actually come from sort of our unhybridized orbitals, although part of the double bond and part of the triple bond does come from a hybrid orbital. That kind of first sigma bond will come from the hybrid orbital. Now, we kind of jumped a little earlier on this, but again, we can obviously apply hybridization to our expanded octets, which is our triangular bipyramidal with 5 and our octahedral with 6. Any questions on that? So again, if you want to apply hybridization, and by the way, a lot of times we do apply hybridization to the central atom, but you can also apply hybridization to outside atoms as well, and it works the same way. So you can apply hybridization to the outside atoms. Typically, again, we don't apply it to hydrogen, but if you had some type of outside atom you want to apply the hybridization, you basically do the same thing. You just count up the electron pairs. Again, the simplest way to assign hybridization is, like I showed you, just mark it off. The good news at this point is you will not be asked to draw the arrows where everybody goes. It's just supposed to help you understand how it accounts for all the electrons. You need to be able to assign hybridization based on your Lewis structure that you draw, but you do need to know, what a sigma bond is and what a pi bond is and what makes up a single bond, double bond, and a triple bond in that relationship. So for example, when you're given something like this, you'll be a professional perhaps here. All right, so apply, we want to know what is the hybridization of all elements except hydrogen. And we also want to know how many sigma bonds are there and pi bonds in the entire molecule. Let's give it a go, see what you come up with. Actually, I want to add to it before you go. Hang on a second. I want to do a retake here. I want to put that. All right, now do it. Little late addition add on there. All right, so we're looking for hybridization to everybody except for hydrogen. And we're also looking for how many sigma bonds total and pi bonds in this entire whatever the heck I just drew. Okay, so let's take a look and see. Again, you can kind of use your little chart here to help you if you need. All right, we'll start here on the left. This guy right here has 1, 2, 3, 4 electron pairs. So 1, 2, 3, 4. Always start at the bottom, work your way up. That is going to be sp3 hybridized. Yeah. Question on that one there. Going to the carbon next to it, that is 1 electron pair, 2 electron pair, and again, that counts as only 1, so that is 3. So that is 1, 2, and 3. So that is a S and 2 Ps, which means it's going to be sp2 hybridized. Question on that one there. Coming to the next carbon, double bond can count as 1, 2, 3. So again, 1, 2, 3. That is also going to be sp2 hybridized. Coming to my carbon next to it, that counts as 1 electron pair. Triple bond counts as only 1 electron pair, so that is 2. So that is 1 and 2. So that's an S and a P there, hybridized. And coming next to it, triple bond counts as 1. Single bond counts as 1. That also is, I'll color it in more, 1 and 2 there. And that also is going to be sp. Any questions on any of those hybridizations? That is how quick you should be able to do it. Yes, it takes a second. Yeah. By the way, we could also apply it to oxygen, right? If I wanted to apply it to oxygen, I got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs, which means I will have 1, 2, 3, and 4. So that is a sp3 hybridization of that oxygen, just like it is in water, basically, exactly like what we saw in water in this case. Any questions on any of the hybridization there? Yeah. It does actually. It can count as essential atoms since there's, yeah. All right, so let's see here. I'm just going to erase some things so we could do the sigma thing and hopefully not erase bonds. Oh, I erased the carbon. That's not good. Put my carbon back. All right, let me pop my carbon back there that disappeared. All right, we're going to look at sigma bonds now, right? In the entire molecule. So basically, a sigma bond is anything that is like a single bond, pretty much. So we'll highlight in yellow, yeah? Sigma bond there, there's 1, there's 2, there's 3, there's 4. Double bond contains 1 sigma bond, right? And a pi bond. There's, I lost track, 5. 6. Triple bond contains a sigma bond. 7, 8, 9, and 10. I think I got them all there. So that is 10 total sigma bonds, if I didn't miss anybody. That's good. Is there another one I missed? That's it's the sp2, so it's not a bond. The one right here. The one right here where my finger doesn't go on the screen. Yeah, the one right there. That's just the sp2. Oh, I missed one on the bottom. No, thank you very much. You're right. And 11. There you go. All right. Thank you. Did I miss any other ones? I hope not. Oh. So actually we have 11 with that one on the bottom. Thank you very much. All right, so now I got all those sigma bonds. So what is left now is our pi bonds, right? And we find pi bonds in double bonds and triple bonds, basically. So we'll go with our pi bonds. This will be a pi bond right there. That's 1. Second line of our triple bond is 2. And third line there of our triple bond would be 3 in this case. So we should have 3. Question on that there. Question on how to apply hybridization, figure out sigma bonds, pi bonds, any of that stuff there. All right. All right. So we're going to then talk about dipole moments here, as I scribbled on this page. Let me erase that there. So what we're going to finish up talking about here in this chapter is molecular polarity. And molecular polarity is basically the entire molecule as a whole. Is it polar or nonpolar? And remember that we did talk a little bit about it when we talked about bond polarity. So when we talk about bond polarity, that is where we use our difference in electronegativity values, and we could draw that bond dipole sort of arrow. And remember that when we're talking about bond polarity, it is really just in reference to between those two atoms, will they be sharing the electrons equally or unequally? When we talk about molecular polarity, we're looking at the entire molecule as a whole, all the bonds that are present. As we did talk about when we did bond polarity, there's only one place where bond polarity and molecular polarity will be the same, and that's when you're only dealing with a diatomic molecule and you just have basically two atoms involved. Now, if you have a dipole moment, that is for polar molecules. And we represent a dipole moment, oddly enough, with the exact same arrow that we use for bond polarity. So we do use this dipole arrow to indicate a dipole moment, and it means kind of the same thing. It just means that this side is negative, this side is positive. What it means in terms of molecular polarity is wherever it's pointing, that side of the molecule as a whole is kind of more negative, and the other side of that molecule is more positive rather than just an individual bond. It's the whole entire molecule as a whole. So polar molecules will have dipole moments. If you have a nonpolar molecule, it will not have a dipole moment. So as we talked about, really your simplest and easiest ones to figure out whether or not something is going to be a polar molecule or nonpolar molecule is our diatomic molecules. And that is because they essentially only have one bond. So if we take something like a homonuclear diatomic molecule, which is a fancy way of saying two of the same elements together, like here. When we look at the bond here in hydrogen, or even the bond here in oxygen, if you do the difference in electronegativity, you are going to get a difference of 0 because they're the same element when you subtract the values. That means in each of these cases, we have nonpolar bonds. And again, as we talked about earlier, because that is the only bond in the entire molecule, that means that this molecule will also be a nonpolar molecule, which basically means we're going to have equal sharing of electrons. It essentially will be a neutral molecule. There's no side of that molecule that's more negative and no side that's more positive in this case. Same thing down here. If we looked at HCl, HF that we talked about earlier, when we look at these bonds here, we will do our difference in electronegativity and we will end up with a polar bond. For example, the difference in electronegativity of this guy is 1.9, which makes it quite polar. Now, because these bonds are polar, and because that is, again, the only bond in the entire molecule, that would make each of these molecules polar molecules. And because they are polar molecules, they will possess a dipole moment that will head towards the more negative side of the atom, which in this case would be the chlorine or the fluorine in the case of the fluorine. And that would be its dipole moment heading in that direction. So again, diatomic molecules are pretty simple to determine. Are they going to be a polar molecule or nonpolar molecule? If the bond is nonpolar in that diatomic molecule, then the molecule will be nonpolar. If the bond is polar, then the molecule will be polar, again, because there's just one bond. So whatever it is basically tells you what the molecule is. When we have three or more atoms involved, you actually have to look at a couple of things. So when you got three or more atoms, you have to look at, are there polar bonds? And secondly, you have to look at the molecular geometry or the shape. So not the electron pair geometry, but the actual molecular geometry of it. So for example, if we look at everybody's favorite example for this, which is carbon dioxide here. And we look at carbon dioxide after we draw its Lewis structure. We know, hopefully, that there are polar bonds in it heading towards the oxygen. By the way, I know that without my table of values, because when I look at the periodic table looks something like this, and they are in the same period, which means oxygen should be more electronegative than carbon, and you don't even need the values to make that determination. So it does have polar bonds. The geometry of this guy is what? The molecular geometry is? How many electron pairs does carbon have? 2. And how many bonds? 2, which means it is linear, right? 180 degrees. By the way, the hybridization of carbon there is carbon is hybridized what? It is sp, yeah? Two electron pairs, 2 letters, S and P, yeah? So in this case, this is actually going to be a non-polar molecule. Now, you may say to yourself, it has polar bonds, shouldn't it be a polar molecule? The answer is because of the geometry, it actually cancels out the sort of polar bonds, if you will. You have basically a straight line, and you have oxygen pulling this way, but you have oxygen pulling the other way. And I'm actually pulling really hard on my pen. My pen is going nowhere. It's kind of like tug of war, right? You got a little flag in the middle. Everybody pulling on opposite sides equal to each other. They actually cancel themselves out. So even though carbon dioxide possesses polar bonds, because of its molecular geometry, they actually cancel each other out, and it will be a non-polar molecule. Now, if we look at something like water, and we look at something like water, water also has polar bonds heading towards the oxygen in this case, right? And when we look at the molecular geometry of water, it is bent or V-shaped, right? It has how many electron pairs, the oxygen? Has 4 electron pairs around it, right? And 2 bonds, that's bent or V-shaped. The hybridization of the oxygen in this case would be what? It's 4 electron pairs, so it should be 1, 2, 3, 4. SP, how many? SP3. Yeah, 4 electron pairs there. So that would be SP3 hybridization. And when we look at this, because the geometry is bent or V-shaped like a V, you basically have electron density heading this way and electron density heading this way. If we want to go back to kind of like the rope example, like a rope meeting at the top, right? So if you pull something from the top, you could imagine the whole thing kind of moving together. And there is a net dipole moment that happens right about there, heading in that direction. And this guy will be a polar molecule where the oxygen side of water is actually more negative. The hydrogen side of water is more positive. That is because these bond dipoles are vectors, they say in physics. They have direction, they have magnitude. And then I fell asleep in physics, but I woke up long enough to know that in certain cases they add to each other, right? In certain cases they basically subtract from each other or cancel each other out. So anywhere where you're heading in equal and opposite directions, basically, they will cancel each other out. Anywhere where you're not heading in equal and opposite directions, they will not cancel each other out. That is, for example, if you added the vectors together, dare I try that? They add together and head net that way, I think, if I did that correctly, there, head to tail. And that's why in water, we end up with a net dipole moment heading through the oxygen. In the case of carbon dioxide, because they're headed in equal and opposite directions, they basically would cancel each other out. So anywhere where you're kind of pulling equal and opposite of each other, they will cancel out. Anywhere where you're pushing kind of in the same direction, they will cancel out. So if you had two dipoles heading right at each other, they would cancel out. You could think of it like a door. You had two people on opposite side door pushing. Door's not going to open, right? So they kind of cancel each other out and stuff like that. So who really wants to draw dipoles and vectors? Not me. So there's got to be a quicker way of doing it, and there is really. And let's just talk about that quicker way really quick here.